goes to the process platform for the conductors, and from this using the rice to by offshore pipeline, and it goes to the floor approach for also receiving station with the spools in between. For example, also if you see oil and gas exploration life cycle, cumulative gas flow, it's like this business is mostly business. Let's see about oil and gas exploration, seismic survey and block identification. They will be doing it, and these are the experts in drilling, reservoir depth, fluid composition, all those things depends. And development concept, the techno-economic feasibility study. We have to study both technical as well as economical feasibility. Project concept also, project definition, development, detailed project report, final implementation. These are all it will come on a development concept itself. Yes, the overall oil and gas wells can be classified into the following three segments. Oil and gas itself, we can classify into three. One is upstream production, transportation, and downstream refining. Upstream production means this is the one what we are talking about, the reservoir assessment and drilling. It's kind of heating, compression, pumping, all these things that would come. Transporting crude oil and natural gas oil, and that's the transportation portion. This will be mostly onshore works. And here you can see oil and gas project segments. If you see upstream production, these are the wellhead platform process production platforms. It's taken from the reservoir and it's taken to the rice. This is the crude transportation. Mostly it's the pipelines and downstream refining. Field development concepts. If you see also field, offshore shallow water fields, sometimes both upstream and downstream activities on land could be optimized to obtain good results, right? Deep water field, shallow water field. Usually shallow water field in conventional fixed platform, it will be provided with the all processing technology similar to onshore consoles. Sometimes special processing also. And also, if you see most latest technology, both also installation and the processing concepts. And dry and wet creek concept. If you see, this is a above the ground wellhead. This is a reservoir, 3 to 6 kilometers, and conductors are and flow pipeline is mostly. This is the dry tree concept. And here we can see above water wellhead. This is in the offshore reservoir. 3 to 6 kilometers. This mostly is also dry tree concept above water wellhead. And this is above ground wellhead, above water wellhead, and subsea wellhead also. It's that is this mostly this is a wet tree concept. Conductor, flow pipe, reservoir, everything is same, but this it will be below the water, so it's a subsea wellhead. And here jacket or jack-up based concept. Wellhead jacket or jack-up rig. This is the drill mast coming from the jack-up. These are the well springs and reservoir. And using the jack-up rigs, it can be done like a wellhead jack-up, jacket and jack-up drilling. Wellhead installation, Christmas tree or wellheads. You can see these are the Christmas tree or wellheads. And subsea template it will be provided, and the well string or reservoir it will be the same as this one. And this wellhead installation, Christmas trees will be here. And Elmos is here in this jack-up drilling. So production platform, if you see well platform and production platform, it will be combined together. And this is also being installed. This is the jacket subsea template based concept. It's a drilling subsea template drilling, coming drilling risers are used to take the freight and well string reservoir. This below the ground surface is the same only. So here we have some floating production also, some subsea compression also there. And then if you go to the introduction also, the water depth, jack-up rigs are suitable for drilling in shallow to moderate water depths ranging from 30 to 120 meters. So 30 to 120 meter we can use jack-up rigs, and jack-up rigs are not suitable for very shallow water. The rigs may not be able to reach the floating mode. Because in the very shallow water we cannot use jack-up rigs. In some cases, swamp barges can also be grounded. Water depth exceeding 120 meter. If it goes 120 meter, the stability of the system will be very critical, as the foundation fixed into the seabed will not be sufficient enough to resist the environmental force. So if it is too deep, then lateral forces will be more than sufficient. Fixity getting at the ground level, it would be a difficult task, and it would be challenging task to resist all these environmental forces. And in deep water, either a drill ship or semi-submersible. You can see drill ship or semi-submersible is used for drilling operations, as no mooring system is required for such systems. Here, if you see semi-sub and drilling ship, there is no mooring up system requirement. The operate with the help of the thrusters and for position tolerance. So it would be having some thrusters for position tolerance purpose. So it would be operating with using that with help of that. And jackup rigs, if you see drilling rigs from form part of the oil and gas exploration activity in offshore for exploration prior to establishing permanent facility for production, temporary structure like that. These are the jackup rigs are temporary structures relocatable, but it's necessary to perform drilling. Jackup with the thrust legs. These are the jackup leg base and rack and pinion concept. And this is the spot can and soft. It will be penetrating the soil until the hot soil it can be taken up until moss, crane boom, helipad, all those things are there. These structures shall have the ease of installation and removal. One such facility is called jackup, right? Jackup is also called the mobile offshore drilling units. So MOD means mobile offshore drilling units. Jackups consist of pontoon, three or more legs to support the pontoon and drill unit. Here you can see this in the plan view. If you see there maybe it can be a three leg or four legs also sometimes it can be. These units can be relocated upon completion of the drilling area at a specific location. Once it goes to the specific location, it can start the operation of drilling, and once the drilling is over, it can be relocated upon completion of the drilling activity at a specific location, right? And backup drilling over the basics you see drill mast, drill pipe, and jacket. These are the jacket bricks and hull, helipad, crane, all those components of this jacket. And if we move away from the shallow water depth, the safety design revolves around the economy and new technology, right? So we'll get process living platforms as a single platform, and we'll get process living platforms separate by distance. You see here it's separated by distance, but here it's a single platform. And offshore complexes you can see as offshore complex. And what it means, like the offshore structure is subject to most onerous and severe loading. So offshore structures will be subjected to strong wind, wave, current, water depth in excess of 600 meter for fixed structures, water depth in excess of 3000 meter for floating structures. So if water depth is exceeding in 600, I mean until 600 meter, we can go with even fixed structures. Anything goes more than 3000 meter and it's not possible to use fixed structure. It's a floating structures operating in temperature far below normal temperature because the seawater will have very low temperatures. So operating temperature will be very far below the normal temperature, right? That's where special materials are required to resist corrosion on because the sea is very much corrosion on. So we need to have some special materials also. Loads are cyclic and fatigue loading will be important because loads are continuously coming from the waves. It will be like a cyclic in nature. It will cause the fatigue loading also. So fatigue loading will be most important thing to be considered while designing the jacket structures of those structures. Also structures subject to most hostile environment you can see here. And as high as the skyscrapers. Comparison of a platform size sky, you can see the skyscrapers. It's almost equal to the skyscraper height. So it can be classified into three, like bottom fixed structures, that's a jacket and temporary structures, compliant structures. Floating structures will be FPSOs, tensile like platforms, articulated towers. That's a buoyant but moored. These are floating structures, but they are moored. Gravity-based structures also there. And types of offshore structures, fixed platform, compliant tower, tensile leg platform, mini tensile leg platforms, power platform, articulated tower, floating protection system, subsea system, FPSOs, concrete gravity platform. These are the different types of offshore structures that we can see in data. You can see these fixed platform and compliant towers, tensile leg platforms, mini tensile leg platforms. Floating protection systems. Also, you can see this is a spot platform. These are moved. These are the floating protection systems FPS and shuttle tanker and floating protection FPS hose. Also, subsea systems are there. And the TPG 500 Unitech semi-submersible spar EDP FPSO fixed platform. You can see fixed platform consists of a jacket, tall vertical section made of a tubular steel members, mostly more steel tubular members supported by piles driven into the seabed, with a deck placed on top of it, providing a space for crew quarters and drilling rig and production facilities. The fixed platform is economical, feasible for installation until water to 500 meter. Until water to 500 meter, we can go with the fixed platforms. That's economical. Platforms can be drilling or processing, and it can be 3, 6, 8. Like see here, it's almost many legs. It can come like 3, like 4, like 6, like or 8, like that. So natural speed of structure varies from 1 to 4 seconds. So this natural speed for this structure varies from 1 to 4 seconds. Compliant tower. Compliant tower consists of a narrow flexible tower and pile foundation that can support a conventional deck for drilling and production operation. Unlike the fixed platform, the compliant tower withstands larger lateral forces, sustaining significant lateral deflection, and is usually used in water depths between 300 to 600 meters. That means like it can go with 300 to 600 meters. We can go compliant hours. It can lateral forces. It can restrain. It can sustain significant lateral deflections also. And generally, four-legged structure with or without guy wires. Sometimes they will use the guy wires like this to control the deflections and they will reduce the lateral forces. The actual period of the platform will be around 20 to 50 seconds. If you see this one 1 to 4 seconds, it's almost 10 times more time, 10, 15 times more. And like platform TLP consists of floating structures held in place by vertical tension tendons. You can see these are kind of strengths. These are the vertical tendons. This is restrained by this. It's held in place by these kind of tendons only. Connected to the sea floor by pile structure templates. These are the pile structure templates. It will be connected to the tendons. And tendons provide the use provided for the use of TLP in broad water depth range with limited vertical motion. So it will not have much vertical motion. The larger TLPs have been predefined what is approaching almost 1.2 kilometer location. Also, this kind of design platforms they have deployed successfully in France. So what we can understand from this one, shallow water means less than 500 meter, deep water is less than 1000 meter, ultra deep water is more than 1000 meters. So less than 500 meters structures with lower natural period range and possibility of bottom water structure that is fixed structure away from severe dynamic loading. So these structures are away from severe dynamic loading and structures can be designed to be rigid. That can we can design the structures to be rigid and held in position. If you see the deep water structure in the upper natural period, dynamics play a vital role. So wherever we go with the deeper water, dynamics also play a role, vital role. Structures are not rigid but lots displacement. So in this kind of flow situation, what such is not the completely rigid like a fixed structure. It can move laterally. So large lateral displacement can be experienced by the structure. So ultra deep water is more than 1000 meters. Usually it's floating and more such as we are using it. So load transfer mechanism, if you see it here, wind load, what are the loads like it's going to come to the structure means it will be experiencing wind load, environmental loads like a wave plus current, and it is the piles are founded in the soft soil layer and it goes to the hard soil layer to transfer the loads. If you see because of these forces, outside gravity load also coming, so pile need to be very large in diameter, difficult to fabricate and drive accurately to the spacing required, right? The piles reaction. So whatever the structure has to be supporting we need to know this kind of file. So we cannot keep much long files just as an execution as a problem. It cannot sustain the displacement. So it's not possible to keep it there. So that's the need. We need to file foundation with the template based. You know, this is like the jacket template. We are putting in the files battered along the orientation of the jacket, providing a large base drivers and reduces loads. If you see here, this will be having the lever arm, so it can, if it's a deep, like it will have more um, resistance. That's why it is sometimes put it in the better system. So base will be having larger width, so it can provide the better stability as well as the related to the price. So design principles of bracket template files. Design bracket assists the installation of files through the large water depth. So mainly function of the jacket, if you see, it assists the installation of file through the large water depth, right? On gravity environmental load basis by supporting the foundation. So the supporting foundation also resisting all these environmental loads plus these are the environmental load as well as this gravity load. Also, pile foundation to be designed for combined loads arising from gravity and environmental loads. So these piles we need to design for this gravity load as well as environmental loads also. Structural design includes determination of global loads on each component and finalizing a steel design per code standards. Okay. What how we have to determine so how much force is this structure each component of the structure is going to experience. So for this structure we need to design in line with the codes and procedures so that it will be safe to transfer the forces. Pile design is to determine the diameter and depth required to transmit the loads to the ground safely. So we need to find out like what is the diameter of this pile is required to transfer the loads also. Safely means it has to satisfy the design criteria. Files should not fail by sharing or unable to bear the loads. It should not have any punching or failure. And either it should be taken as a either it should be taken with a strong layer or enough It will transfer the loads. Either it should be taken to the strong layer, means in the strong layer it will have a lot of bearing, and in case of friction flash, if it's taken to the large depth, it will resist through this here. Freestanding piles, freestanding pile, surface piling template. You can see some sample. Vertical main pile, vertical, this is a main pile. Flannery is between the jacket and there's a pile is a grout, ungrouted here. In this case, here it can be grouted or ungrouted. Battered main pile or main pile through the leg. You can see the mud pad, seabed, soft clay, medium clay, dense sand. This kind of sample details you can be seen. Battered main pile and battered skirt pile. You can see the skirt pile, vertical skirt pile, battered skirt pile, and vertical skirt pile. We can have different concepts, configurations, welded platforms, process platform sample. So when do we opt for a floating structures? So water depth going exceeding 500 meter, then we have to go for floating structures. Design installation of fixed structures become uneconomic and practically impossible. So with this high water depth, it's really going to be uneconomic and practically impossible for the fixed structures to be designed and installed. So we need to go for the floating structures for economic purpose. Also in normal conditions, possible to relocate to safe areas in case of extreme normal conditions of operations permit. Yeah, especially if it is a floating structure, it can be relocated to safe areas. Large topsoil loads, with the topsoil loads are very huge, and then pile foundation capacity and footprint of this superstructure. That also it's limiting, right? So we need to go for this floating structures. If it is a very large topsoil loads for the weight and size, what can they designed for? They can be designed for drilling, production, storage. FPSO, right? Introduction. FPSO is a floating storage offloading. FPS floating production storage. This is the production storage and offloading also. So structural design play a major role in the oil and gas field, right? So especially the structural design kinds of design of members for joints for static or cyclic load. The like design against cyclic load is called fatigue design. So when we design joints members against cyclic load, that's for basically we are designing it for fatigue design. Analysis and design of cyclic loads requires understanding of the following topics: hydrodynamics, sea state, material selection, structural response. So these all these concepts we need to be understanding to design the also structures. Fatigue evaluation methods, we have fracture mechanics, cumulative damage method, and fatigue damage. So usually cumulative damage method we used to do it for using the palm minor rule. These things we can see it. So fatigue location. Failure by fatigue can occur at any location along the member or its connection to other members, along its member or at its connection to the member. Location of alternating stresses here, depending on here the material member fatigue location, wave forces. It's the deflected shape of the member. When it goes front and back, it can be alternating stresses. It can develop at here, so it can experience tension as well as compression. So this kind of alternating location of alternating stresses. So in the deflected shape of the member, you can see it very clearly. This number is going to be alternating. So these kind of locations, it can have the fatigue failure. Usually the failure will occur where there is a change in the geometry or load path. Where there is a change in the geometry as well as load path. It can be taken two locations. Member fatigue and flow thickness change location. See here, this location, usually here, this location will be having very high, heavy wall thickness, and this location less wall thickness. So this location there is a change in the wall thickness. So member fatigue that these thickness change locations needs to be studied, and joint fatigue that the geometry change locations. Here, if you see this geometry itself changing, so it is connecting to the tubular to tubular. So when the geometry change location, joint fatigue, and then member thickness change location, member fatigue. Fitting in offshore structures. Fitting in offshore structures is very common as the structure is made of a steel with predominantly hollow circular section, open sections, plate connections, following broad areas interest like the tubular connection, thickness transition.